Good morning, everyone, and welcome to this webinar dedicated to hydrocarbon solvents in the pharmaceutical industry. Before we start, I'm going to explain how the platform works. The webinar is recorded so that you're going to receive the recording a few days after the webinar. You're all on mute and the camera is off, but in any moment, if you have a doubt or do you want to ask a question, you can use the chat that you found at the bottom of the platform. At the end of the webinar, there is a Q&A session, and we're going to try to answer as many questions as possible. In case there is not enough time to answer all the questions, we're going to reply to you anyway via email in the following days. These are the speakers for today's webinar. I am Camilla Tronti and I'm in charge of marketing and communication. The second speaker will be Luca Pigat, who is Business Developer Manager for the pharmaceutical market. And the third speaker will be Jérôme Boom, who is the Sales Director for MPPE and TIPPS technologies. This is the agenda for the day. After a quick introduction, we're going to talk about Veolia Water Technologies Italia and the pharmaceutical industry. Then we're going to dive into the core topic of today's webinar, which is MPPE technologies and its application in the pharmaceutical production. And after, we're going to talk about some case studies related to this application. As mentioned before, we're going to have a quick Q&A session at the end of the webinar. For those of you who doesn't know us, we are part of the group, Veolia Group, which is a French multinational company with a worldwide presence. Veolia Group has three main core business, which are water, energy, and waste. Through its three complementary activities, Veolia helps to develop access to resources, to preserve them, and to replenish them. Veolia Water Technologies is a subsidiary of Veolia Group, and it's the leader in water treatment. Veolia Water Technologies designs and supplies drinking water, processed water, and wastewater treatment plants, as well as most standard water treatment units for municipal and industrial application. Moreover, Veolia Water Technologies has a series of service, a full range of service to provide our clients everything they need. Veolia Water Technologies in Italy has three offices and two main divisions. The first one, the project and services, customized solution for water and wastewater treatment application, odor control, and biogas production. The second one, the solution division, develops standard technologies for wastewater treatment. Okay, and now I hand the floor over to Luca, who's going to talk about Veolia Water Technologies Italia and pharmaceutical industry. Thank you.
Thank you, Camilla, and welcome to all of you to this new webinar. I'm really glad today to drive you into the application of MPPE technologies for manufacturing context. Well, MPPE means macroporous polymer extraction, and this is one of the Veolia patented technology for the industrial wastewater treatment. In this picture of introduction, you can see the full range of Veolia technologies applicable to the wastewater. Example, if we look on the top left, there is evaporation or evapoconcentration, mostly used in pharma industries to treat, for example, the wastewater from the first rinse in washing recipes. That with the evaporation, we can reduce up to 95% the amount of the wastewater with a low temperature separation between distillate water that could be reused and the rest of 5% or less of concentrate liquid to waste offsite. Another one is on the bottom left, useful in pharma for sure, is NBBR, that means moving bed biofilm reactor. There are suspended carriers with a biofilm to perform a biological treatment in which the biomass that is adhered to the carrier is able to specialize itself for absorption of selected API. Well, MPPE is focused on the treatment of residual solvent, and today we will see some case studies of application. Now, in general, please keep in mind that wastewater treatment is no longer just about focusing on the end of the pipe. Action are increasingly taken upstream to deal with more challenging issues at their source. Well, the first time when I saw the list of organic hydrocarbon solvent that MPPE technology already treated in an installation, well, I said it's great because most of them are used also in the pharma industries. So we can apply NPPE to the wastewater treatment in pharmaceutical manufacturing in Italy, in Spain, in more cases than before. We can solve many situations in your industries of chemical synthesis, for example, that before had no ways to be solved with a treatment on site. Today you will learn about case studies of treatment of toluene, of dichloromethane and isopropyl alcohol. Here in this slide, I brought only a partial of the list from MPP experience. So from the pharma point of view, as a first step, I made a cross-check between this list and the table of list in the solvent from the guideline ECHQ3, the revision 6, that is the guideline for impurities control and residual solvent in the final medicine. This guideline is useful to our webinar because it reports a classification of the solvent used in the pharmaceutical production. The classification is based on the evaluation of, for their possible risk, the risk of the solvent residual to the human health. Let's see, it goes from class 1, that are the solvent to be avoided in terms of residual in the medicine. Class 2, solvent to be limited. In the guideline, and not in this slide, there are also class 3, solvent with low toxic potential, and a class 4, about solvent for which no adequate toxicological data was found. So in the list that MPP technology is successful, we can find names from class 1 and class 2 of the guideline, the worst case. And now I propose to have a quick survey about technologies that you may have already in your plant. So please, we can start with a survey and the question to you. Take your time to answer and see. Well, of course, essential medicine such as antibiotics, blood thinner, and pain relievers require solvent in their manufacture. So you already use them, and for sure you already treat them in some way. The administration of many essential medicine would not be possible without solvent, as medication must be applied as ointment, swallowed as a syrup or injected as a liquid. So solvents are uniquely able to dissolve the medicine safely and effectively into basic formulation. And which solvent is chosen depends mainly on the different physical properties of the molecule. So based on your question, we will see information from you, from the list of people you are. No? And I think that now the time for answer. Now you're still answering, so we will wait. Well, this webinar will be focused on organic hydrocarbon solvent. And let's see the time. Hydrocarbon solvent, we know, are petroleum derivatives used in the cleaning and dissolving substances. To design properly a treatment solution for the wastewater with residual solvent in the peculiarities of application in pharmaceutical industries, modern technology, we also must assume some basic consideration about why solvents are used in the pharma, where the solvents are used, and the segregation of contaminated flows upstream the wastewater treatment plant. And some note consideration about the concentration of the solvent in the streams. So the organic solvent generally are used as reaction media, as separation and purification of the synthesis product, and for cleaning of equipment. So use as medium, as the carrier in which the chemical reaction take place to make the API, no? Or used to separate the desired chemical product from unwanted ones, maximizing the drug purity, as we saw in the guideline. And for cleaning also it's important of primary packaging. Drug packaging typically contain a complex mix of chemicals that comes from the production manufacturing that could compromise the biologically safety and efficacy of the drug. In short, solvent can be used either as a part of the reaction or as a carrier or for purification. In pharmaceutical industries, we focus on high purity hydrocarbons from 95 to 99%, and as some supplier of solvent propose up to 99.75%. The high purity in particular allows efficient and targeted control of the subsequent synthesis step. Well, the final medicine product could be potentially contaminated with organic solvent in the phase of synthesis or the extraction or the fermentation to produce the API, the purification, of course, and the dilution in liquids, the granulation, a film coating for the oral forms or the primary packaging. So sometimes the source and means of contamination determine the way of removing them and reducing their quantity. And for our scope of today, the identification of the point and source of contamination of the wastewater from the production. As told before, the key point must be the segregation of contaminated flows upstream the wastewater treatment plant. One of the cases is API chemical synthesis manufacturing, as most of you are. Here on the left side, there is a simplified block diagram of the process and segregation nodes of point in which the solvent can contaminate the stream of the wastewater. On the right side, a similar one for the extraction process. These show to you a very basic way that we use to prepare a water mapping of the pharma industries at the beginning of the design. Well, MPPE, you will see in the picture of running installation, is a modular skid technology. So it is perfect with the design and modularization of a synthesis plan. And I will say that more than API, now the focus could be on high potent API due to the rising demand for oncologic drugs. As we saw that in the coming years, the market for HP, for high potent API, is expected with a growth rate of 8-9%. The production of high potent API pose a risk to the worker and to the environment. So along with the high potency, HP API often exhibit high cytotoxicity. Therefore, efforts to prevent contamination are essential to to a safe manufacturing process which guarantee the well-being of the environment. So in case of chemical synthesis, the designer of the treatment must be able with the end user and engineering to identify the points of adding solvent into the reaction vessel, into the purification step, and the phases and the equipment in which the removal of solvent comes, and the primary contamination of wastewater streams from scrambled from purification. So each step should be mapped with a flow chart, a diagram, and to describe the flow and the characterization of the wastewater stream. Now the last point, last comment will be on the concentration of solvent into the wastewater stream. Just a few considerations that the concentration is proportional, of course, on the removal of solvent from the raw medicine. The level is not only based on the values of toxicity written in the guideline ECHQ3, but it is also specific of each medicine formulation, means of each manufacturing plant, each batch, each kind of production batch. So could be that apart from the fact that residual solvent have no therapeutic values or might be toxic, they might additionally accelerate decomposition of the product. The presence of residual solvent at levels well within acceptable limits could entail the risk of inducing phase transformation and jeopardizing the physiochemical stability of active substances, and finally the quality of the dosage form. Additional argument for removing organic solvent from the drug product could be the odor and the taste of the chemicals, which are not good drug attributes for sure. Well, I finish here my presentation that had the aim to develop application opportunities for MPPE technology in the pharma manufacturing context. So now we are going to see technology detail and running installation. Thank you.
Thank you, Luca. Thank you for your interesting speech. Now, as you mentioned, we are gonna hand the floor over to Jerome, who's gonna talk about MPPE and its application in the pharmaceutical market.
Thank you, Camilla. First of all, for all the attendees, thank you for joining. So we are going to discuss on this MPPE/MPPS technology and how it can be applied in the pharmaceutical market. But first, I would like to introduce our business unit. So we are part of Veolia Water Technologies. We are based in the Netherlands, and our core business is removal of hydrocarbons. We originate from the oil and gas industry, so I will show you some old references from that industry. But we are now slowly moving into pharmaceutical applications, also in semiconductor applications. From our office in the Netherlands, we supply complete solutions to clients. We do from there we do the field services of the units that are in operation. It's also the facility where we produce the media which we are using in our technologies, and it's a very specific type of media. It's fairly unique. And of course, we have our lab facilities for, on one hand, quality control for the media production, but also testing a lot of new applications for clients. Furthermore, we store some mobile units we can send on site for testing purposes, and I will show you an example of that later. First, a few words on hydrocarbons. The term hydrocarbons, Luca already indicated it to some extent. Hydrocarbons or solvents, as more often used in pharmaceutical, or oil types of oil, which is also a designation for the type of components we are removing. These type of hydrocarbons come in two kinds. One is the dissolved kind, and one is the dispersed kind when you mix these hydrocarbons with water. In case of dissolved hydrocarbons, it means that every organic molecule is fully surrounded by water molecules, and it gives you a clear solution, like the ethanol or the alcohol in the vodka. On the other hand, we have the dispersed or free hydrocarbons, and these form either layers on top of the water or small droplets. And since we have these two type of hydrocarbons water presence, we also have two types of treatment technologies to deal with that. So for the dissolved hydrocarbons, we use MPPE slash MPPS. And for the dispersed hydrocarbons, we use conventional TIPS technologies, so tilted plate technologies. We will not discuss those. We will stick to the MPPE and MPPS. So, as Luca indicated, the abbreviation MPPE stands for microporous polymer extraction. And basically, we use this technology to remove the dissolved hydrocarbons by means of liquid-liquid extraction. And from the little quiz we did previously, I noticed that a substantial part of the attendees are familiar with liquid-liquid extraction. The only thing what we did is we basically immobilized the extraction liquid inside the particle. And by doing that, you're enabling the use of extraction liquid in an easier way, and you can pack it in particles inside a column or a vessel. So the extraction mechanism remains the same, but we just wrap the technology in a new package. On the right, you see some pictures of the media. So these are cylindrically shaped particles. They are approximately 1 millimeter in length. But if you look carefully with an electron microscope to it, then you will see that the structure is extremely porous. And what you have to imagine that all these pores are filled with the extraction liquid. And numerically, roughly 70 volume% of the particle contains a liquid. So if you have these particles in your hand, you're basically holding liquid in your hand. The type of extraction liquid we are using is a kind of oil, and that means that if you bring this media in contact with wastewater that contains non-polar hydrocarbons, then the hydrocarbons will distribute between the water phase and the extraction liquid inside the particle. And the ratio at which they do this is called the partition coefficient. So if you have a molecule that really likes to be in the extraction liquid, you will find a very high partition coefficient, and that component will be easy to be removed. If you look at polar components, then this is not working too well, because polar components, they feel happy in water and they are not very eager to migrate into the extraction liquid. So for those components, we cannot use this technology. However, we have been looking for different types of media which also can extract polar components, but this is not much based on extraction, but rather on sorption. And I will give some examples of that as well. Let's have a closer look on how we apply the technology and the operation principle. So we have the media which is packed inside a column, a steel column, and we have a feed flow containing hydrocarbons, and we push it in an upward direction through the column, and treated water will leave the column at the top. And basically all the hydrocarbons which are present in the feed will be captured by the media. Well, you can imagine that this cannot continue forever, so at some point we need to regenerate that media, and that's we are doing by applying low pressure steam in downflow direction through the column, and by doing that we are heating up the column, and the steam together with the released hydrocarbons, we send them to a condenser and then to a separator. And what you will see is that the organics, they will, together with the steam, condense, collect in a separator. And if you have components that have a limited solubility or are not miscible with water, then you will see that the hydrocarbons will form a layer on top of the separator water content. So we can skim off the hydrocarbons as a pure component, and the water in the separator, that will be recycled because that will still contain high levels of these hydrocarbons we are removing. So if we look at the system as a black box, then we see that the feed water is coming inside the system, the treated water is leaving according to the specifications as agreed. We push a little bit of steam inside, and we recover the hydrocarbons as a pure component. Now, that means that our systems we have in operation in the field always contain two columns. One is in extraction mode and one is in the regeneration mode. If you look at the steam consumption, then we use approximately 0.5% of the feed flow. That means for treating 1 cubic meter of water, we use approximately 5 kilograms of steam. And that is relatively low compared to some of the other technologies that popped up in the quiz, being distillation and steam stripping. So this is a fairly energy saving type of technology. The projects we have in place, most of them, they target a very high removal efficiency, up to even 99.95%. That also means that in some cases we can bypass an azeotrope for some components that form azeotropes with water. As explained, we recover the hydrocarbons as a pure product. In some cases, it's even has some value, so it's not just waste; it might have a value. As in some cases, it is indeed a waste, but then the stream of it, in terms of tons per hour, is really low, so it's very concentrated. We don't use any chemicals. We don't produce any other waste or sludges. And in general, the technology is fairly simple. The units do not require a lot of operator attention. And just to give you an example, some of our references are operating in the oil and gas industry on unmanned platforms in the North Sea. What you see in this picture is a glass separator vessel in one of our demonstration units, and you can clearly see the hydrocarbons on top of the water phase. And the water phase, again, it is still very polluted, but we basically mix it with the feed water again to be reprocessed. And we can do that because the flow of this water phase is relatively small. Just to remind you, we're using 5 kilograms of steam for the regeneration, so it's relatively small percentage of the feed flow. There's one note to be made here, and that is that in case you're dealing with components that are fully miscible with water or have a very high solubility, then of course the trick of having a separate layer of hydrocarbons will not work. It will simply be a mixture of the hydrocarbon and water. And in that case, the whole inventory of the separated vessel becomes a waste, or could be a product that needs further upgrading by external parties to recycle the solvent. Now, for lots of you, it might be a fairly new technology what I'm presenting here, but in fact the technology has been around for quite some decades. But like I said in the introduction, our foundation is in the oil and gas industry. So therefore, I would like to share two references with you, just to show you that on one hand, the technology is proven, and on the other hand, that it is regarded as very reliable. So the first reference we ever put in operation, that was in 1994 at a site in the Netherlands, Vermilion Energy. And that is a site where gas is being produced and extracted from the ground. And that gas-produced water contains a lot of BTECs, so benzene, toluene, ethyl benzene, and xylenes. And in order to operate this plant, the client had to treat the wastewater to a very low level of BTECs, being less than 0.5 ppm, while the inlet is approximately 2000 ppm of BTECs. This unit has been in operation for almost 25 years. It just did not make its 25th year anniversary on a few months, but at least it shows you it's an established technology. The other example I have is also for gas-produced water, which is one of our main focal points over the past decades. In this case, it's a unit, a very large unit, treating 140 cubic meters per hour on a big FLNG, a floating LNG facility of Shell in Australia. And this boat, it's one of the biggest boats mankind ever built. It was a $15 billion project, but it relies on our technology to discharge the water in accordance to the permit of 30 ppm of hydrocarbons, which can be discharged overboard. So this whole project is depending on our technology, just to show you that it's by the oil and gas industry, it's regarded as a reliable, proven technology. So about some additional words on the polar components. Again, with extraction, we cannot remove components that are very soluble in water. The components like to stay in the water and do not move into the extraction liquid. So for that, we need to do something else, because we did get a lot of demands from the market, also outside oil and gas, like pharma, like semiconductor, to remove hydrocarbons. So we said, well, we have to be looking at a kind of media that will basically absorb these hydrocarbons, but which can be applied in the same way as we do for the extraction liquid. So here you see a list of components that was present in groundwater from a pharmaceutical company in Switzerland. And as you can see on the left, we have some of the usual suspects like BTECs, which can also be removed by MPPE. But we also see a lot of polar components like acetone, THF, MIBK, etc. We tested different types of media, and finally we selected one type, and that is now being used for the MPPS, so the microporous polymer sorption processes. And you can see that also for these components, an extremely high removal efficiency is obtained, except for two components. If you look at methanol and ethanol, the values listed here, then you will see that the removal efficiency is very poor, or it's actually even erratic. Sometimes we do remove somewhat, sometimes not at all. The reason for that is ethanol and methanol, they are very much alike water, and there's not sufficient discrimination between water and those two molecules. So those components we will not be able to remove, but besides that, most organics will be removed by this technology. So now, since I've introduced to you the technology, I would like to do a quick quiz. So can you pull up the quiz? Because I will show you some case studies in which we have applied this technology in the pharmaceutical industry. But for me, I would be interested to find out from your side what would be the main drivers to potentially apply this technology. can we have the quiz, or is there a small issue? Otherwise, we do the quiz after the case studies. I propose to move further with the case studies and do the quiz afterwards. Okay, so applications we are looking at. Sorry. Are listed here, and again, there's a distinction between MPPE and MPPS. On the left, you see the more non-polar or oleophilic components that are being removed by the extraction media, and on the right, you see the adsorption media tackling all kinds of polar components. Before we can apply the media, the feed water should be meeting some requirements. First of all, the feed temperature of our wastewater stream should be limited. In case for the extraction media, it should be less than 40 degrees. For the sorption media, we can tolerate a bit higher temperature up to 60 degrees. You always should realize that the lower the temperature, the better the performance, and that is the reason that is caused by the fact that we have basically a temperature difference that does the regeneration. So the larger the temperature difference, the better removal efficiency we get. In terms of pH, there is some limitations on the extraction media, 4 to 9. That is the limit we would like to apply, not to damage the material and not to leach out the extraction liquid from the particles. Again, the sorption type of media can handle higher pH ranges. And then for both technologies, we have a limitation on TSS, total suspended solids. And the reason for that is that I explained to you that we put the media inside a vessel as a packed bed. And you can imagine that if you have a lot of turbidity or particles in your feed water, that bed will be plugged and there won't be any flow through the bed anymore. Then the final requirement, which is in the little box at the end, it's a very important one. Because we use steam regeneration to regenerate the media, we have to look at components that have sufficient volatility. And that can be expressed, for instance, in the boiling point. And typically, as a rule of thumb, we would say a boiling point should be less than 200 degrees centigrade. Otherwise, we cannot regenerate it. So if your components have no volatility, for instance, organic acids, then it's something we cannot, we can remove it, but we cannot regenerate the media. And for that, the media is simply not suitable. I now realize that we should now do the quiz on potential drivers. Now you should understand the technology and the do's and don'ts for the technology. Is it now possible to put up the quiz, or? There it is. So if you look at the projects we have done in the past, but also looking at the new leads that come in on a daily basis, I'm interested to see what could trigger you to implement the technology or consider the technology. So it's either recovery of solvents, meeting wastewater discharge criteria, or save on costs of water treatment. And save on cost on water treatment includes also bringing wastewater offsite, because I noticed in the first quiz by Luca that quite some streams are sent offsite to a third-party disposal. So Well, it seems that recovery of solvents is of lesser interest, but meeting wastewater discharge criteria and the cost saving is of course always a driver. It's good to know. Of all these, I will show you some examples in the next days case studies. So the first case study we are looking at is for a pharmaceutical company in Scandinavia, and this company had the production of an ingredient for to deal with the skin disease, and this production process generates a toluene-loaded stream, and this stream also contained the API of interest, and that would be further processed downstream by amongst others a membrane process, and in order to protect those membranes, the toluene level had to be very low. The client had already had this production process on site, and they previously used steam stripping to remove the toluene from this mixture, and they were not happy with it, and in particular the fouling and the downtime resulting from cleaning that fouling, that was a major headache, and that had partially to do with the fact that inside the steam stripper there were certain hotspots where a lot of chemical reactions were ongoing and causing this stripper to foul in a relatively short time. Furthermore, the client wanted to extend their production line, so they were looking for an alternative technology doing the same job, but cheaper and less operational input. So we proposed the technology to them, and of course they were not familiar with it, so they wanted to have it tested first. And the first test was done in our lab facilities in the Netherlands. We received from them two batches of 1 cubic meter of wastewater, and we have been using our micro unit to treat it. The picture on the right shows you the micro unit. So it's a fully automated MPPE unit. It's just very small. So we have the two columns, one in operation, one in regeneration, and we have all the surrounding utilities like cooling water for the condenser. We have the heat exchanger, etc. So everything is there, and it's running fully automatic also overnight if necessary. Furthermore, we invited the client to witness the test. We often do that. Clients appreciate it a lot. They can see how it works. They see the actual results. So this was done now approximately 4 years ago, I think. And here are some results. First of all, what was noticed is that the feed water was very turbid. It contained small droplets, and that was very clear when we did the analysis of the feed water, because it contained up to 1100 ppm of toluene. Well, the solubility of toluene is only like 500-600, so there's also dispersed toluene present. And if you look at the feed water and the treated water, the two little bottles on the top right picture, then you can clearly see that the first one is turbid and the second one is very clear. The second one still contains the color, but that is actually the product that the client wanted to recover. If you then look at the graph, then you can see that the removal efficiency in these tests was extremely high. So we have a loading cycle of 1 hour, and you can see that throughout the full hour, the recovery, or the removal efficiency of the unit is very high, well above 99.99%. For us, toluene, we know it from the oil and gas industry. We have a lot of projects on toluene removal. So for us, it was not a surprise. It's one of the more easy components to be removed. Then in the separator of this micro unit, you can clearly see that after some time, a layer is formed, and that is actually the layer of toluene, which eventually can be skimmed off. So the client was happy with the results, and we built a full-scale unit on basis of this principle. In this particular case, the client want to have it as a separate unit near the tank farm. So we built a containerized unit, and here you see the columns with the media sticking through the bottom of the top container. The toluene is recovered as a high concentrated liquid, so it's almost pure toluene. It's sent to a third party. And yeah, if you compare this with the stripper system, we are looking at approximately 60% energy reduction in this particular case. And again, these energy reduction numbers, they are very dependent, of course, on inlet composition, inlet concentration, and capacity. So it's not a generic number, but in this particular case, it's definitely that range. A second example is for the removal of IPA. So IPA is also a solvent used in the pharmaceutical industry. And in this case, the client is producing a wastewater containing IPA from a washing process, and the feed concentration was initially established to be 1 to 1.5 weight%. Actual values show even values of 2 weight%. And the idea was to recover the IPA because the client felt that it was better than to oxidize it or convert it to sludge. So we did the bench scale test again to start in our lab, and for us, we knew that we could remove IPA very well because we have an operating reference in Taiwan in the semiconductor industry, where IPA is used as a washing liquid for the wafer production. So we were quite confident, but obviously the client needs to be convinced as well. So we did some bench scale tests, and again we found a high and very consistent removal efficiency of 99%. So we have, let's say, an inlet of approximately 10,000 ppm and an outlet in let's say the ppm range, but actual values on actual analysis on IPA showed even lower numbers. So the next step is a pilot on site, and this pilot is currently being executed. Here you see it's a 20-foot container. That's a pilot we use, which is complete autonomously. So it has its own steam production to regenerate. And eventually we will be treating 8 cubic meters per hour. The location is already prepared for the full scale. And again, the IPA that will be concentrated up to a value of a minimum 20%. In this particular case, this stream was previously sent to a third-party treatment company, and that allowed significant cost in reduction if we can reduce this amount of wastewater to be sent externally. But also the logistics of trucking away these amounts of wastewater is, of course, significant. Then one final example. This is also an older reference. It's on the removal of DCM, dichloromethane, and in this particular case, it was related to groundwater treatment. Of course, pharmaceutical companies they do not like to be associated with fouling and environmental issues, but in this particular case, there was a clear relation between the activities and the state of the groundwater, and we were requested to see if we could remove these components, DCM, but also other chlorinated hydrocarbons as well as aromatics, and to remove these and basically return clean water back into the ground. So this is something we have been doing for 10 years on that side, and that after that 10 years the levels were sufficiently low. But another reason to show this example is that although this was purely a groundwater unit, groundwater treatment unit, we also have an example in which we not only treat the groundwater, polluted groundwater, but also some streams from the production. So the technology is fairly flexible to deal with different types of different levels of concentrations and fouling. In this particular case, DCM is a component with a fairly low partition coefficient. That means that it's difficult to remove from water, and that the migration from water into the extraction liquid is not going that fast. That's why the columns are relatively big. Maybe nowadays we would do it with MPPS, because in that case the whole column and the whole system would be significantly more compact. But that's I would say progressing inside. I think that's the end. So I would give the floor back to Camila.
Thank you, Jerome. That was really interesting. Okay, so here we are in the Q&A session. Let me check if there is any question. Okay, yes. What is the lifetime of the media and what happens with it when it doesn't work anymore? I think, Jerome, you can cover that.
Yeah, so that's a good question. The media we are using, the different types of media we are using, basically we always take it back after when its lifetime is ended, and the lifetime depends very much on the type of application. If you look at some of our oil and gas applications where we are treating relatively clean streams, then the maximum lifetime we ever observed was 7 years. But typically, I would say it's between 2 and 4 years. If there is an application where the feed water is, let's say, less defined and contains a lot of other things outside the organics, then it can be reduced. We had one client which had a lifetime of only 6 months before, but they really pushed every waste stream they had. They pushed it through the unit because it was cheaper than exporting it to a third party. So they were fine having a frequent replacement of 6 months. But like I said, typically I would say 2 to 4 years. And once the media has lifetime is ended, then we take it back and we either dispose of it in an appropriate way, or in some cases, in cases of clean applications, we actually can rejuvenate the media. So we make sure that there's a sufficient extraction liquid inside, that the particles are clean from dust and deposits. And then actually the media is simply reused. So from that point of view, it's a fairly sustainable way of applying media for wastewater treatment.
Okay, thank you. Let's move with another question. Can the technology be used to capture APIs from wastewater?
Yeah, APIs are troublesome components, but they are often present in, let's say, relatively low concentrations, and often these are fairly complex, large molecules. And especially the latter is for us a difficulty, because we will not be able to generate them, because they simply will stick on the media and will not come off during the steam regeneration. So from that point of view, it could be used, but I doubt whether it's the most efficient way of dealing with APIs. It's more that we like to target the solvents, etc.
Okay, we still have 1 minute, so I'm gonna ask the last question. What are the economic benefits of using this technology?
Well, so the one of the main benefits, if you compare it, for instance, to steam stripping or steam distillation, is the energy consumption. It's much lower. Again, depending on a case-to-case basis, we can evaluate that. But so from OPEX point of view, it's a very cheap technology compared to others. And yeah, in some cases, like in the IPA removal, we can clearly see that for this unit, a return on investment of less than a year is possible simply by saving on costs of disposing and trucking away wastewater and invest in a unit that actually treats it.
Okay, thank you. I think that was all. So thank you everyone for participating into this webinar. You're going to receive shortly afterwards a satisfactory survey that we kindly ask you to fill in, since it's very important for us. And that's all. Thank you all for attending. Have a nice day.
Thank you.
Thank you.